All right. Now we are going to start section 2.3, which is on isotopes and atomic mass. And we've already talked about atomic mass some. And I've really already touched on isotopes some, but we're going to more formally define it here. Okay, so let's go back and let's revisit carbon. Right, let's say that I have a carbon atom that has 6 protons and 6 neutrons. Right, 6 protons, 6 neutrons. Now, we've already established that this has a mass number of 12. But what if, let's say hypothetically, I had a carbon atom with 6 protons, or let me make that a more generic statement, and let's just say that I had an atom that had 6 protons and 7 neutrons. Right? It's still carbon, but now this one has a mass number of 13 AMU. Right? And then let's say that I had 6 protons and 8 neutrons. This is now going to have a mass of 14 AMUs. All right. Now, all 3 of these are carbon. They all have 6 protons. They have to be carbon. But they are not exactly the same atom. Chemically, they are going to behave very, very similarly. In fact, depending on exactly what you're doing, they behave identically. Their reactivities are the same. Sometimes they do have, some of them do have some different properties, but effectively, chemically, they're the same, except they do have these numbers, different numbers of neutrons. We call the relationship between these isotopes. Remember this word. Now, as I always like to do, let's break this down. Let's look at this prefix. The prefix iso means same. Okay. Isotopes are atoms of the same element with different numbers of neutrons. Right? So, for carbon, just for example, I have these 3 common isotopes. And yes, these 3 isotopes do exist. I call this one carbon 12. This one is carbon 13. This one is carbon 14. Now, we have a simpler, kind of more expedient way to write this, and this is something called the nuclear symbol. Now, to write a nuclear symbol, I write the elemental symbol. So I'm going to give this for this whole series with carbon. But we could make this a little bit more generic, and I will give a few more examples of this. So to write the nuclear symbol, I'm going to write the elemental symbol. So that's the symbol on the periodic table for carbon, that's C. To the bottom left, I am going to write my number of protons. Now, I realize that's a little bit redundant, but for what we're going to do when we get into nuclear equations, that is going to make this a lot simpler and a lot easier to keep track of. Right, so if I have, so to the bottom left, there again, going to write the number of protons, 6 for all three of these. And now to the top left, I'm going to write my number of, or I'm sorry, my mass number. So for carbon 12, I'm going to put a 12 here. For carbon 13, I'm going to put a 13 here. For carbon 14, I'm going to put a 14 here. If I have, just for example, chlorine, I could write chlorine 1735, and then my other common isotope of chlorine is chlorine 37. Bromine, just as another example, 35, and then 79 for one isotope. 81 for the other isotope. Now, will you be expected to know these mass numbers off the top of your head? No. But if I give you all the information to write a nuclear symbol, you'll have to write them. If I give you a nuclear symbol, I'll expect you to be able to tell me number of protons, number of neutrons from it. All right. So let me also make another point out of all of this. If you notice, so when we looked at the atomic mass on the periodic table, for chlorine, we saw that it was 12.011. I'm sorry, for carbon, it's 12.011. For chlorine, it was 35.45. And for bromine, it was 79.90. I mentioned that we can't get that to go directly to our most common, or we can't use that to go, can't necessarily use it directly to find our mass number for a given atom. If we were to look at the naturally occurring abundance of carbon, I would see that about 98.5% of naturally occurring carbon is carbon 12, about 1.1% is carbon 13, and about 0.4% is carbon 14. When I look at this 12.001, that is actually a weighted average of all the isotopes and their relative abundances in nature. Same deal with chlorine. This 35.45 comes from the fact that I have about a 3-to-1 ratio naturally occurring of carbon 35 versus, or I'm sorry, of chlorine 35 versus chlorine 37. For bromine, 79 and 81 occur in roughly equal proportions. A little more carbon 79 than, or I'm sorry, bromine 79 than bromine 81, but that is where that number comes from. All right, so that's that for nuclear symbols and for looking at isotopes.